My first exposure to physics came in high school when I decided to make a physics engine for a project. As with many of my projects, I bit off way more than I could chew, but I still learned a lot. At the time, I did not have the experience needed to actually write the code, so I just kind of threw things together until the compiler stopped yelling at me. I never got it to put anything on the screen because that's the job of a rendering engine, but I did have all the parts needed, including a collision detection system, both broad and narrow, and I had a numerical integrator. The collision detection detects if two objects have collided, and if they have, it moves them apart. On the other hand, the numerical integrator basically does all the physics simulations, so it's the one that's actually moving objects around on the screen. While collision detection is interesting in its own right, I want to focus on the numerical integrator. More specifically, how switching two lines of code around somehow drastically improves performance and stability. Before I get into the video, I just want to say that I'm going to be speedrunning numerical methods and classical mechanics in the context of game dev, which means a few things. First, I'm going to be focusing on situations that actually occur in video games, which means I'm basically going to be ignoring all of these things. The first part of the video will be a recap of basic game dev style physics and numerical methods. The second part of the video will be explaining Hamiltonian mechanics, and the third part will be using Hamiltonian mechanics to derive symplectic integrators like the one in the thumbnail. Since you can find a lot of resources on game dev physics and setting up Hamiltonian mechanics online already, I'm not going to cover them into too much depth. As I go through the video though, I will recommend resources explaining them in more depth for those interested. If you're not comfortable with calculus or Taylor series, you should definitely watch 3 Blue 1 Brown's series, Essence of Calculus, especially the video on Taylor series. You should also check out 3 Blue 1 Brown's video, Differential Equations, A Torus Sky. This video is a good overview of how differential equations work and how to simulate them numerically. With that out of the way, let's get into the video.
Let's begin by talking about coordinates. Coordinates are a set of numbers that describe a point in space. For this video, we're going to be working almost entirely in Cartesian coordinates, where each coordinate represents how far you go in a specific direction. You can see an animation of Cartesian coordinates on the screen right now. Note that none of the lines change direction, which makes Cartesian coordinates simpler to work with for a physics engine. Coordinates can describe points in spaces other than physical space. In fact, if you can put numbers to things, you can create a new space with coordinates made from the numbers. For the vast majority of games, you'll want to work with systems that are best described using classical mechanics. In classical mechanics, your goal is to figure out what path the objects will take through space by considering all interactions and constraints between the objects. Mathematically, this process involves finding and solving the equations of motion. The solution to the equations of motion gives the path of an object as a function of time. In classical mechanics, there are 3 main methods to find these equations of motion: Newtonian Mechanics, Lagrangian Mechanics, and Hamiltonian Mechanics. Most game engines use Newtonian Mechanics because it's the simplest to implement, and game physics doesn't need to be too accurate as long as it's not obviously wrong, or if it becomes part of the charm. In Newtonian Mechanics, you express all interactions and constraints in terms of forces, where force is equal to mass times acceleration. You then add up all the forces on an object to get the net force. Then, since force equals mass times acceleration, and acceleration is the second derivative of position with respect to time, you get a vector differential equation for each object. You can break each differential equation into a differential equation for each coordinate in space. These differential equations are the equations of motion. Now that we have the equations of motion, we just have to solve them. In high school and even some college classes, every problem that you can solve has a closed-form solution. For example, you may be asked to solve this system of equations, factor this polynomial, or find this integral. For each of these problems, there's a solution you can write out explicitly in terms of simple functions and operations. These are closed-form solutions. On the other hand, there are many problems that do not have closed-form solutions. To give a few examples, this integral from statistics and probability, this differential equation that shows up in the Kepler problem, and this polynomial do not have closed-form solutions. We have to look for the next best thing: a numerical approximation. With a numerical approximation, we set some maximum tolerance for error and try to come up with a solution that will stay within that tolerance. To find these approximations, we use the field of numerical methods. It's a huge field with a lot of different approximation methods for a lot of different subfields in math. For this video, we're going to be focusing on approximating the solutions to differential equations, which is also known as numerical integration, because integrals undo derivatives according to the fundamental theorem of calculus. Going back to our problem, we want to come up with numerical approximations for these differential equations. These equations are second order because they have second derivatives. Before we can get to second order differential equations, we're going to have to look at first order differential equations. The prototypical first order differential equation is this. The solution of this differential equation is x as a function of t. For a physics engine in a video game, we don't know this function ahead of time because we don't know what forces are going to act on an object. For this reason, a lot of standard techniques aren't viable, so we'll need to do a Taylor series expansion. I'm not going to explain where Taylor series come from or why they work, so check out this video if you want to know more. For now, we're just going to use the idea that Taylor series can approximate a function around a point using the value of the function and its derivatives at that point. If we know the initial value of x and t, which we'll call x0 and t0, we can plug it into the differential equation to get the derivative at that point. We can then plug this derivative into the Taylor series to estimate x at a different time, t1. We'll call this new x, x1. Since we have approximations of x1 and t1, we can use that information to calculate the derivative at that point. We can then use the Taylor series expansion to calculate a new x at a later time t2. We'll call this new x, x2. As you can imagine, we can keep doing this process for as long as we like. At the end of this process, we can write our approximation of x as a function of time by plotting each point t and x in. In this way, we've come up with the first and simplest numerical method for solving differential equations. Euler's method. Euler's method is pretty awful on its own, but it's a base for most other methods. To improve the accuracy, you use smaller time steps, use a higher order method, use an implicit method, or use a predictor-corrector method. For the highest accuracy, you often use multiple methods. I want to run a series at some point on numerical methods that would cover these topics, but for now I'll just give a brief summary of these ideas. The time step is the difference between tn and tn plus 1, and we denote it with a delta t. As the time step gets larger, the real function diverges more from the Taylor series approximation. Using a smaller time step leads to a more accurate approximation at the cost of having to do additional steps. To minimize the amount of time wasted, there are a lot of adaptive methods that use smaller time steps when it needs to and larger time steps when it can get away with it. Alternatively, you could use methods that use a higher order approximation of the Taylor series. The order in a Taylor series refers to either the highest degree of the time step or the highest order derivative in your approximation. By using smaller time steps or a higher order method, you can exploit Taylor's theorem. In English, as long as your higher order derivatives don't get too crazy, higher order methods with smaller time steps approximate your function with less error. Up to this point, we've been working with explicit methods. These methods work by taking in the current value of the function we want to approximate along with some other information to calculate the value of the function after a time step. With implicit methods, we use the value of the function after the next time step to calculate the value of the function after the next time step. It sounds confusing, but we just solved this equation for xn plus 1. While implicit methods provide a better approximation than an explicit method of the same order and tend to be more stable, solving for xn plus 1 often requires far more work than using a smaller time step or a higher order method. To get around this problem, we tend to use an explicit method to estimate xn plus 1 and then plug that result into the corresponding implicit method. The idea is that the explicit method should be a decent approximation of the solution, so plugging the result of the explicit method into the implicit method should give a better approximation. In this scheme, we call the explicit method the predictor and the implicit method the corrector. It's all well and good, but our equations of motion for the physics engine have second derivatives. We can deal with second-order differential equations by creating a new function and setting it equal to the derivative of the function we want to find. We can then replace all second-order derivatives with the first derivatives of the new function. We're doing physics, so the function we want to solve for is the position. The new function is the derivative of the position with respect to time, which we call the velocity. We can then treat the position and the velocity as their own separate things, except when updating the position. With all that said, we have three things we need to do to update the position and the velocity. We have to calculate the acceleration, add the velocity times the time step to the position, add the acceleration times the time step to the velocity. Now all we need to do is figure out which order to do the steps in. As long as we calculate the acceleration before the velocity, we have something valid, so we have three possible orders. The equal sign means set the variable on the left equal the value on the right. The plus sign just means add the value on the right to the variable on the left and store the result in said variable. There is a subtle difference between these methods. In the first method, we use the old position and the old velocity to calculate the acceleration, then we use the old velocity to update the position, and then use the acceleration to update the velocity. The second method is similar, but it uses the new velocity to update the position. The last method uses the velocity to update the position before calculating the acceleration, which it then uses to update the velocity. While the first method is known just as Euler's method, the last two methods are known as semi-implicit Euler methods. We call them semi-implicit Euler because they use half the results from the next step to compute the next step. Unlike a full implicit method, they don't need to solve any equations to find the next step. To figure out which method to use, we're going to try all of them on a spring system, where the force is given by Hooke's law. The expected behavior is that the spring goes back and forth like a sine wave. If we test all three orders, we have the following results. As you can see, the first method is blown up while the other two methods seem to be doing alright. In fact, we could let this system run as long as it wanted and you wouldn't notice anything weird.
So what's going on here? How does switching the order of the steps make an unstable method stable? To answer that question, we're going to need Hamiltonian Mechanics. Before I get into Hamiltonian Mechanics, I want to talk about Lagrangian Mechanics because it's an intermediary between Hamiltonian and Newtonian Mechanics. If you want to know more about Lagrangian Mechanics, I have a few articles in the description below. Newtonian Mechanics is perfectly valid for classical mechanics, but it has a big problem. To work with non-Cartesian coordinates in Lagrangian Mechanics, you either have to explicitly or implicitly work with the Christoffel symbols. Earlier in the video when I said that the Cartesian coordinate system is better for physics engines because the directions don't change, this is what I was talking about. In Cartesian coordinates, the coordinate system doesn't change, which means all the Christoffel symbols are zero, which means your equations look nice and simple. In the same way you rarely construct a formal bijection between a set of objects and the natural numbers to count something, you rarely calculate the Christoffel symbols directly. As you can see in the 3 blue 1 brown video, Differential Equations A Torus Guide, you can find the equations of motion for a pendulum without bringing in the full formalism of classical mechanics. You do need to bring in D'Alembert's principle, however. D'Alembert's principle says you can ignore all parts of all forces in the direction of a constraint. In the case of the pendulum, you can ignore all parts of the forces that compress or stretch the beam. While D'Alembert's principle is useful on its own, Lagrange wanted to speed up the process. The entire derivation of Lagrangian mechanics will take roughly 40 minutes of math that I'm not going to put into this video, so again, check the articles in the description if you're interested. At the end of all that math, you get this thing called the Lagrangian, which you can plug into the Euler-Lagrange equations to find the equations of motion. In most cases for a classical particle, the Lagrangian has the form of kinetic energy minus potential energy. You get one Euler-Lagrange equation for every coordinate in your system, which is nice because if you pick your coordinates correctly, you can often ignore some of the equations of motion because they don't change or do anything. To see how Lagrangian mechanics works, let's try to apply it to a pendulum. The kinetic energy is defined as 1/2 mass times velocity squared. In Cartesian coordinates, it has this form. We'll want to convert it into polar coordinates because the length of the beam isn't changing. The two main ways to find the kinetic energy in different coordinate systems are to either find the metric tensor, or you can just substitute your coordinate transforms in. In either case, you get this as your kinetic energy. Moving on, let's talk about the potential energy. The potential energy is related to your force, and it shows up whenever your force only depends on position and doesn't get too weird. Formally, the force must be the negative gradient of some function. Going off of high school physics, the potential energy in this case is just mgy, where y is the height. Since we're doing everything in polar coordinates, we could write the height as -r cosine theta, where theta is this angle. At this point, we can write out the Lagrangian. Finally, since the length of the pendulum isn't changing, we can set r dot equal to 0, which means r has to be a constant. Just so you don't think that r is still an active coordinate, I'm going to label it as L. Since the Lagrangian only has one actual coordinate, we only need one Euler-Lagrange equation. Plugging the Lagrangian into this Euler-Lagrange equation gives us this equation of motion. Now, this is a simple example that you could use Newtonian mechanics for without too much trouble. For systems more complex than a pendulum, Lagrangian mechanics becomes almost necessary. If you don't believe me, try finding the equations of motion for a spring pendulum and a double pendulum using Newtonian mechanics and Lagrangian mechanics, and see which one takes less effort. To save yourself some trouble, you can use D'Alembert's principle on the double pendulum to ignore some of the constraint forces, but doing that's kind of an admission that you really want to do Lagrangian mechanics anyway, so whether you count that as Newtonian mechanics is up to you. So we've got Lagrangian mechanics set up, but we won't be able to use it for this problem, at least not directly. While it often makes finding the equations of motion easier in many cases, it doesn't really do much more beyond that. Maybe you can use Noether's theorem to find conserved quantities by looking at certain symmetries of the Lagrangian, but that's pretty much all you're getting. Maybe there's some more advanced stuff with Lagrangian mechanics that I don't know about, but to actually answer our question, we still need Hamiltonian mechanics. Like with Lagrangian mechanics, I'm not going to explain how to derive Hamiltonian mechanics because there are already videos talking about it, including some linked in the description below. With that being said, I'm still going to describe how you find the equations of motion using Hamiltonian mechanics. In Hamiltonian mechanics, you find the Lagrangian, do a Legendre transform to get a new quantity known as the Hamiltonian. I'm not going to explain the Legendre transform or anything like that because this video is already long enough. If you want to know more, check out Andrew Dotson's videos in the description. For the forces you'll see in video games, the Hamiltonian is just the total energy. To find the total energy, you add up the kinetic and potential energies. Unlike Lagrangian mechanics, Hamiltonian mechanics works with the momenta, not the velocities. For us, this means we have to take what we got from the Legendre transformation and replace all the velocities with the momenta. In classical mechanics, momentum is mass times the velocity, which means our kinetic energy is 1/2m times the momenta squared. Since we're only dealing with forces that would show up in a video game and are working in Cartesian coordinates, our kinetic energy is this. If you do some more math that you can see in Andrew Dotson's video, you end up getting Hamilton's equations, which are like the Euler-Lagrange equations, but for Hamiltonian mechanics. To see how Hamiltonian mechanics works, let's try to find the equations of motion for a spring. The kinetic energy is 1/2m times the momentum squared, Well, the potential energy is 1/2 kx squared, where k is a constant. To get the Hamiltonian, we just add them together. Plugging the Hamiltonian into Hamilton's equations gives us these equations of motion, which are exactly what we would have gotten if we had just worked with Newtonian mechanics. Okay, so the Hamiltonian approach doesn't do too much for us when talking about a spring. Using Hamiltonian mechanics on a spring, though, is kind of like bringing a nuke to a gunfight. For a more natural problem, let's try to apply Hamiltonian mechanics to something that Newtonian mechanics would have struggled with, a pendulum. Since we're not working in Cartesian coordinates, the momentum is a little bit different. To find it, we have to use the formal definition of momentum. To find the momentum, we take the derivative of the Lagrangian with respect to the angular velocity. Then we do the Legendre transform and substitute the angular momentum in every time we see the angular velocity using the relationship we described earlier. At the end, we have the Hamiltonian. Plugging the Hamiltonian into Hamilton's equation of motion gives us exactly what we would have gotten if we had just done Lagrangian mechanics. Let's just recap what happened. In the Hamiltonian approach, we had to find the Lagrangian, then use the Lagrangian to find the momenta, then do a Legendre transform so we could find the Hamiltonian, then plug the Hamiltonian into Hamilton's equation to get the same exact equations of motion we would have gotten if we had just done Lagrangian mechanics from the start. In the Lagrangian approach, we find the Lagrangian, plug into the Euler-Lagrange equations, and we're done. This was my first experience with Hamiltonian mechanics, and I'm willing to bet it was your first experience too. Few textbooks at the undergrad level give examples where Hamiltonian mechanics really stands out. Every presentation of Hamiltonian mechanics at the undergrad level says there's this thing called the Hamiltonian that you get from the Lagrangian, you plug it in Hamilton's equations to get the equations of motion, and then you realize that you could have saved so much time by just doing either Newtonian mechanics or Lagrangian mechanics. Even in more advanced cases, a lot of the stuff you cover isn't really to the fullest depth, it doesn't really show off why it works. So you have books mentioning things like Poisson brackets, but they only talk about the basic properties without giving any kind of reason why you'd care about them. You get things like Liouville's theorem, which is pretty useful in like an abstract sense as the base for a lot of other things in stuff like statistical mechanics. And the last thing you tend to get is something about phase space in quantum mechanics, but like, again, they're all just like, these things exist. So you get things like, phase space exists and is incompressible, and that's important for reasons. Poisson brackets exist, and they have this cool algebraic structure. We're not going to do anything with it though. And I get why they do it. Most modern physicists tend to work with quantum mechanics or thermodynamics, and not necessarily advanced classical mechanics. And all the topic these undergrad approaches tend to cover show up in either thermodynamics or quantum mechanics. When you add the fact that Hamiltonian mechanics also requires a lot of mathematical maturity, it becomes pretty hard to convince yourself to actually talk about it in any depth, instead of spending that time on more immediately useful things. Luckily for you, the viewer, my time is worthless, so we're going to cover Hamiltonian mechanics in depth. This is the part of the video where we're going to get into some mathematics and physics few of you will have seen before. At the end of the day, all we're doing is approximating Taylor's series like we've been doing throughout this video, just with some Hamiltonian mechanics added. More specifically, we want each update of the position and momentum to be a canonical transformation. To ensure we have a canonical transformation, we need Hamilton's equations to be satisfied in the new coordinates. To do so, we're going to start with Hamilton's equations in the old coordinates, convert them to the new coordinates, and then impose Hamilton's equations on the transformation. To start, we're going to convert our time derivatives of the old coordinates into time derivatives of the new coordinates using the multivariable chain rule. The multivariable chain rule says you take partial derivatives with respect to every input times the time derivative of every input, and then add them all up. For this video, I'm ignoring any time-dependent transformations. If I wanted to include them, I'd have to add a time derivative term. Since the new coordinates are functions of the old coordinates, we can use the multivariable chain rule to get this relationship. Just to keep notation clean, we're going to rewrite everything in terms of matrices, which gives us this result. Now we're going to insert Hamilton's equations into this transformation. In matrix forms, Hamilton's equations can be written like this. We can then substitute the matrix into the equation to give us this. For the last step, we want to convert the derivatives of the old Hamiltonian with respect to the old coordinates into derivatives of the new Hamiltonian with respect to the new coordinates. To finish off the process, we again use the multivariable chain rule. This matrix shows up so often that it has a name, the Jacobian. The matrix we found in the first step is just the transpose of the Jacobian. For this result to satisfy Hamilton's equations, we need this matrix product to equal this matrix. This matrix doesn't really have a name, but it's usually denoted with a J if you're doing physics and an omega if you're doing math. So this should be it. This is how you check if a transformation is canonical. To test it out, we can find the Jacobian for each of our three algorithms, plug it into this equation, and see the results. as you can see, the bad Euler method is not symplectic, while both semi-implicit methods are symplectic. At this point, we've technically answered the question in the thumbnail. The two semi-implicit Euler methods are better because they use canonical transformations, while the bad Euler method does not. If you're like me, you're probably not satisfied with this explanation. While we've answered one question, we've introduced several more. For example, would it be possible to find the semi-implicit Euler method without trial and error? Another question to ask would be, does semi-implicit Euler work with every single force that could be described by a Hamiltonian? Furthermore, is semi-implicit Euler the best we can do? Are there other symplectic methods? There's also a big problem with the fact that we don't have established error bounds with the semi-implicit Euler method. We know that semi-implicit Euler works better than Euler based on the examples we've tried, but we don't have strong guarantees on the error bounds. If semi-implicit Euler doesn't blow up, how does the error manifest in our approximation? I'm going to spend the rest of the video answering these questions by working with a Poisson bracket. To work with a Poisson bracket, I have to explain where it comes from and why we care about it. Let's say that instead of just looking at the position and momentum as functions of time, you want to look at an arbitrary function of position and momentum as a function of time. We'll call this function f, and it could be anything. In some cases, this function turns out to be a position or momentum coordinate in another coordinate system, like angular momentum, for instance. In other cases, we'll want to check if some function stays constant over time. For our specific problem, it'll turn out to be a vector of all the position and momentum coordinates, but we'll get there when we get there. To solve for this function as a function of time, we're going to take the time derivative of that function. To do so, we're going to again use the multivariable chain rule. Since f is an arbitrary function of position and momentum, it takes in every position and momentum coordinate as an input, which means its time derivative is this. If f were also a function of time directly, we would also have to add in a time derivative term over here. We're going to completely ignore this case for the video because I don't want to write it out, and because we're doing game dev physics, so it's probably not even there in the first place. Using Hamilton's equations, we can replace time derivative terms in this expression with derivatives of the Hamiltonian with respect to the position and momentum coordinates. Apparently, expressions like these came up in Poisson's work so often that he decided to invent the Poisson bracket. The Poisson bracket has this definition. Using the Poisson bracket, we can rewrite the time derivative of f as the Poisson bracket of f with the Hamiltonian. The Poisson brackets have an algebraic structure that can make life a lot simpler. The Poisson brackets form a Poisson algebra, which is a special case of a Lie algebra. The rules of a Poisson algebra are given here. First, it's anti-commutative, which means if you flip the order of its arguments, you flip the sign. It's also bilinear, which means it's linear in both arguments. Linearity means that you can scale or add inputs before or after the transformation and get the same results. In the case of a Poisson algebra, it means you can factor constants out of the bracket, or turn a bracket of a sum into a sum of brackets. It also satisfies the Leibniz rule, which is similar to the product rule you learned from calculus. It also satisfies the Jacobi identity, which I don't have anything to say about because no one does, it's just the Jacobi identity. You just see it pop up sometimes. If anyone has a good explanation of what the Jacobi identity is or why it keeps popping up, please let me know in the comments below. Lastly, if and only if you're working in canonical coordinates, the following relationships hold. Basically, the Poisson bracket of position and momentum coordinates is 0, unless if you're dealing with position-momentum coordinate pair, in which case it's 1. Using these rules, you can prove a lot of things. For example, the Poisson bracket of a function with a momentum coordinate is equal to the partial derivative of that function with respect to the corresponding position coordinate. Likewise, the Poisson bracket of a function with respect to a position coordinate is equal to the partial derivative of that function with respect to the corresponding momentum coordinate. This fact is particularly important because it gives us a quick and easy way to evaluate Poisson brackets. Now that we've set up all that abstract stuff, let's get to the problem at hand. Let's say we have some function that takes in the time and spits out the position and momentum coordinates as the output. If we take the Taylor series of this function with respect to time, we should be able to get a numerical approximation for the position and momentum coordinates of every single object. To apply Hamiltonian mechanics to this problem, we can convert the Taylor series into a Lie series by replacing all the time derivatives with Poisson brackets. If we take the first order approximation in this form, we get the bad Euler's method. So how do we get a symplectic integrator out of this mess? Let's look back at the general formula for a Taylor series. If we rearrange it a bit, we can pull out everything but the function and turn the Taylor series into an operator. If we then replace the t minus t0 with a delta t, then we get the shift operator. It's called the shift operator because it shifts the input of a function. We usually represent the shift operator in a different form. To find it takes a leap in logic and some abuse of notation, but it's still mathematically sound. We can think of taking higher order derivatives of a function as repeatedly applying the differential operator. Informally, we can do so by raising the differential operator to a higher power. If delta t is a constant, then we can combine it with the differential operator, which becomes us taking powers of delta t times d dt. If you know your common Taylor series, you should be able to recognize this as e to the x, but with x replaced with delta t times d dt. This is the usual form of the shift operator, and it's what you'll see in basically any discussion of symplectic integrators. If taking the exponential of the derivative doesn't really make you feel comfortable, check out 3 Blue 1 Brown's video, Flammable Mass videos, and Dr. Payam's videos. If you still want to know more, check out any of these series on Lie algebras in the description below. To bring it back to Hamiltonian mechanics, we replace the time derivative with the Poisson bracket with respect to the Hamiltonian. We're using a dot as a placeholder for whatever we're applying the shift operator to. This placeholder is a little iffy though, it still feels weird, so we're going to replace the Poisson bracket with the Hamiltonian operator. This procedure of making things into operators is way more common in quantum mechanics because everything's already an operator in quantum mechanics. It still works in classical mechanics though. Now that we got in this form, is there anything we can do with it? For a moment, let's say the Hamiltonian is separable, which means you could write it as the sum of a function of the position and a function of the momentum. Separable Hamiltonians tend to show up when you're working in Cartesian coordinates, and your forces are all functions of position. For most of the forces in a video game that the numerical integration pipeline handles, the Hamiltonian can be written as the kinetic energy, which is purely a function of momentum, and the potential energy, which is purely a function of position. Since we've already converted the Hamiltonian into an operator, we might as well convert the kinetic and potential energies into their own operators. Just as with the Hamiltonian, these operators represent Poisson brackets with kinetic and potential energies. Going back to the time shift operator, we can split the Hamiltonian operator into kinetic and potential energy operators. We can then split up an exponential of a sum into a product of exponentials, which means we apply the operators one after the other. Both of these operators are symplectic, which you can prove using the test given earlier in this video. To figure out the results of these operators, we need to convert everything back into Poisson brackets. To apply the potential energy operator to the position coordinates, we take the derivative of the potential energy with respect to the corresponding momentum coordinates. Since the potential energy doesn't depend on the momentum, all these partial derivatives go to 0, which means the position doesn't change after applying the potential energy operator. To apply the potential energy to the momentum coordinates, we take the partial derivative of the potential energy with respect to the position coordinates. In first order terms, this gives us the negative gradient of potential, which is just the force. In other words, our first step is to add the force times a small time step to the momentum. Since momentum is mass times velocity and force is mass times acceleration, you can cancel out the masses to get acceleration times a small time step plus the velocity. Then we apply the kinetic energy operator. The Poisson bracket with the kinetic energy and the momentum coordinates is 0 because the kinetic energy does not depend on the position, which means the momentum doesn't change. The Poisson bracket with the kinetic energy and the position, on the other hand, gives you the velocity, which means we add the velocity times a small time step to the position. Note that we've already updated the velocity, so we're using the new velocity instead of the old velocity to update the position. In code, we represent this by adding the new velocity times a small time step to the position after we've updated the velocity. If we go back to our 3 Euler algorithms, we can see that this code matches one of the 3 variants we came upon earlier. To get the last variant, you apply the kinetic energy operator before you apply the potential operator. Alright, so we're done with the video, right? Not quite. There's a small problem I've swept under the rug. As you might suspect, by the fact that applying the operators in a different order gives a different algorithm, switching the order of the operators doesn't exactly give us the same result. I lied a little about how you split exponentials of sums into products of exponentials. That statement only applies if we can switch the order of the operators and get the same result, which we can't in this case. To see why, we can convert the exponential shift operator back into its Lie series form, and expand everything out. Then, we can take the difference between the two. I'm only going to do the expansion to second order. If you calculate the difference between the terms to higher orders, you get the Baker-Campbell-Hausdorff formula. Working with it is so tedious that Baker-Campbell and Hausdorff didn't even derive the formula, they just proved that a formula existed. If we keep all terms up to second order, we get this. If we then convert these into operator forms, we get this. We can then plug it back into the exponent. Lastly, we can introduce this concept known as the commutator, which you'll see a lot more of in quantum mechanics. In this form, you can see that while we are doing symplectic transforms, we're doing it with a slightly different Hamiltonian called the shadow Hamiltonian. This fact means that energy isn't exactly conserved. With that being said, since the original Hamiltonian and the shadow Hamiltonian only differ by a small amount for a small time step, the actual energy of the system is approximately conserved. Now that we've discovered the shadow Hamiltonian, we can actually talk about how the error manifests. In many common cases, the difference between the shadow Hamiltonian and the real Hamiltonian leads to symplectic integrators giving you the right path through space, but usually at the wrong speed. For example, springs and other systems that go back and forth will move at a slightly different frequency. Since most gamers don't care about high precision estimates of the spring constant, you shouldn't care either. So semi-implicit Euler beats Euler for simulating a lot of physical systems, but what about those higher order methods I mentioned earlier? While some of them can produce more accurate results for a while, their use of non-canonical transforms leads to a significant energy drift. While symplectic integrators still have error, they don't have the same energy drift that you see in non-symplectic integrators. Furthermore, the errors of symplectic integrators tend to be less noticeable than the significant energy drift that you see in non-symplectic integrators. For these reasons, symplectic integrators tend to be a much better fit for video games than non-symplectic integrators. For similar reasons, physicists tend to prefer symplectic integrators over non-symplectic integrators in their research. As a specific example, when looking at whether or not a system is chaotic or not, what really matters is the path through phase space, not necessarily the speed at which it moves along the path. Since symplectic integrators better approximate the paths objects take through phase space, they're used in studies of chaos, more specifically under what conditions a system becomes chaotic. Speaking of higher order methods, is it possible to create a higher order symplectic method? The answer is yes, but the process is a little weird. To construct a higher order symplectic integrator, you take the shadow Hamiltonian of your current integrator and try to get rid of the lowest order terms that don't show up in your real Hamiltonian. For example, take the shadow Hamiltonians of the semi-implicit Euler methods. We want to get rid of this delta t times the commutator term. If we look at both of them, we see that one of them adds delta t times the commutator, and the other one subtracts delta t times the commutator. If we therefore do one semi-implicit Euler method, and then do the other semi-implicit Euler method, we cancel out this term. To get it back to just one time step, we divide our original time step by 2. In terms of exponential operators, the process looks like this. I'm being a little imprecise because I don't want to do the full Baker-Campbell-Hausdorff formula, but this is the basic idea behind Verlet methods. These Verlet methods are second-order symplectic integrators and tend to perform pretty well for separable Hamiltonians. To find other higher-order methods, you look at the various products of these exponential operators. If you want to see what that process looks like, you can check the link in the description for more info. All in all, for most video games, semi-implicit Euler should be good enough, but if you want more precision, you could do a Verlet integrator. So now it's time to ask the final question of the video. How well do symplectic integrators work for video games? A lot of important forces can be written in terms of potential energies, including constant accelerations like gravity, spring forces, attractive or repulsive forces that are based on the distance from a point to an object, and many more. There are also a lot of forces in video games that cannot be represented with a separable Hamiltonian in the scheme that I've presented. These forces include drag, damping, impulse forces like jumps, collisions, objects getting destroyed, and so on. For many reasons, you don't use the numerical integration pipeline to simulate these forces. For drag and damping, you multiply your velocities by a number between 0 and 1 and let exponential decay do its work. If you absolutely need a more accurate simulation of drag, like if you're doing a flight simulator, you could put the force in explicitly and it'll probably be fine because losing energy tends to be stable, though you might want to double check. For impulses, you just add the impulse to the velocity. For elastic collisions where objects bounce off each other without losing kinetic energy, you use an explicit formula. For inelastic collisions, you use a different explicit formula. For objects getting destroyed, you transform the object into a destroyed state, or you hard code in where the object's going to break beforehand. Hamiltonian mechanics can handle forces that vary slowly with time. Look up adiabatic invariance for more information. Those forces aren't a problem. On the other hand, forces that vary quickly over time cause problems for pretty much every single integrator you're doing, so you don't really put them in video games. While this is not a complete list of every single force you could see in a video game, it does include most of the forces you would see in a large variety of different video games, including first-person shooters, action-adventure games, puzzle games, and so on. In short, most of the forces you're dealing with in video games can be written in terms of a potential, in which case they can be handled by symplectic integrators, or they're just not part of the numerical pipeline, so you don't need to worry about them. Well, that was a lot, and I left a lot more out. To help fill in the gaps, I'm going to recommend some resources on the various topics I've covered in this video. For more information on numerical integration and game dev, check out Glenn Fielder's Game Physics series. For a practical example of how to use differential equations in other ways in video games, check out Tesslator's video, Giving Personality to Procedural Animations Using Math. For more about game development in general, check out these YouTube channels. For more information on physics in general, check out my series, The Road to Quantum Mechanics, in which I rigorously explain all the concepts that led up to quantum mechanics. Unfortunately, I have not finished writing The Road to Quantum Mechanics. I'm about a third to halfway through it. If you can't wait for me to finish those articles, check out V.I. Arnold's Mathematical Methods for Classical Mechanics. It's one of the best textbooks that actually covers Hamiltonian mechanics in any depth. If you want to know more about Lie algebras, which includes the stuff we do with Poisson brackets and the Baker-Campbell-Hausdorff formula, I'd recommend the collaboration between Michael Penn and Tom Rock's Math, where they talk about the relationship between Lie algebras and the Heisenberg uncertainty principle. That video is just an intro, though. For a more in-depth discussion, check out Richard E. Borchard's series on Lie algebras. Unfortunately, it's incomplete, so I'm going to list a few other playlists on the screen right now. Lastly, if you're just interested in numerical methods, the textbook by Burden Fairs is a pretty standard textbook in the field, and it's the one I learned from. That's it for me. If you have any questions, concerns, or things you want me to cover, let me know in the comments below.
See you later.